This video, we're going to simply define what it means for a radical to be in simplest form. Okay, so the whole intent of this video is to be able to take a radical expression and write it in simplest form. So we say for a radical to be in simplest form, we must not only apply the properties of radicals, but also remove any perfect nth power. So first things first, we need to remove any perfect nth powers other than 1, and we need to rationalize any denominator. So here are some illegal things. We say things that we don't want to be true about radical expressions. So like this would be one of them if we had a radical in the basement. So illegal in the sense that this would be undesirable. If we had an expression like this, yuck. Okay, so here's us. Okay, we don't want roots in the basement. And we also say, like, if I had an nth root and I had like a to the n on the inside of this and I didn't, simplify that, I didn't call this a, then I would say that I have a perfect nth root in here, or nth power that I could take the root of, that I just haven't done it yet. Okay. So what we're going to do is we're going to work on simplifying some radical expressions, just kind of show you what I mean. So when it comes to simplifying radical expressions, and you have like just, we say the cube root of 54, the first thing that I'm going to suggest you do is when you don't have a fraction, like on letter B here, let's take this 54 and actually let's reduce it, or at least let's try to factor it. So I notice it's even, like, so like 2 times 27. I say, well, 27, right? That's 3 times 9, and then 9 is 3 times 3. What we're going to do is we are going to write this in a way that we call the prime factorization for 54. So the prime factorization is what you get when you take a number or an expression and you break it down into all of its parts until you can't break it down anymore. It's got to break down into primes. So when you rip a number apart into its prime factorization, we could really just state how many of each type of factor did we have. So for instance here, I say, how many 2's did we have? Well, we had 2 to the first because I had 1, 2, and then I have some 3's. How many 3's did I have? So I had 1, 2, 3. So I say 3 to the third. Now this is essential in simplifying this, because what we're going to do is this. We're going to take out any perfect nth roots. And we notice here that in this case our index n is 3. So I'm saying basically this. We say, all right, well, how many groups of 3 can you make me of each of these types of things that you have in here? In other words, is there anything you took times itself 3 times to get, what you got? Okay. So I noticed that this is going to work with our 3 right here, just to point things out. We have a group of 3 here, but basically we'd start and we just go through this one by one. We'd say, all right, well, I've got 1, 2, 1, 2. Here's like our lonely 2. Can you make me a group of 3 factors of 2? And we don't have any other factors of 2 to fill in these other spots. So we say, no, this 2 is stuck on the inside of this cube root. Now when you look at the 3, we say, all right, well, really, I mean, if I rewrote this, I say 3 times 3 times 3. How many groups of 3 can you make me? And I can make one group of 3 3's right here. So what we're going to do is we're going to cross that off. We'd say, all right, I'm going to take one group of 3 3's out front, and this represents the number of groups of size n, of this size that you removed of that factor out of the inside. So we say, how many 3's do I have left on the inside? Now, suppose I do want to make this comment. We could write 3 to the 0, which technically is 1, but it's not necessary to do so. What we did was we ended up with this expression here. We say 3 times the cube root of 2, which is what we had left over. So again, we're going to try this again with a fraction, okay, a little bit different. And this is going to involve rationalizing, but a little bit different than how we've done in the past. So for instance, if we say 2 over the square root of 3, what we had to do in the past was we had to take the top and the bottom of this times the square root of 3, and what we get is 2 root 3 over just, square root of 3 times square root of 3 is just 3, and that was efficient at getting rid of the radical in the basement. This is a little bit different, because what we need to do first, by the way, is split this up into the, the root of the top, the fifth root of the top, over the fifth root of the bottom, okay? And then we're going to take my advice like we did in the last one. What we're going to do is we're going to factor everything on the inside of the top and inside of the bottom. Now, 3 is a prime number, so we're going to write 3 to the first. But down here, I'm going to say this is the fifth root of, now when I factor this, I get 2 2's, so it's really 2 squared. So what I want you to understand is this. If I were to give myself a little bit more room here, first of all, if I were to want to get rid of, say, this radical in the basement, I could try, I could try to multiply by the fifth root of 2 squared on top and bottom. That would be like how we've rationalized in the past. But I want you to notice this. On the bottom, you would get this. You get the fifth root of 2 to the fourth. You'd multiply the stuff on the inside of these two things. And the thing is, that's not a perfect fifth root. So what we're really going to do is we're going to rationalize with these 2's here. I don't mind writing these fifth roots of 2 in. So we're going to say we're going to multiply the top and the bottom by the fifth root of 2, just like we've done in the past. It's just that I'm going to ask this question: how many more 2's would I need to add on top of this 2 to add up to a full group of 5? And so the quickest way to get there is to just take it times the fifth root of 2 to the third. So what we end up with is this. We're going to multiply straight across. The interesting thing is we get the fifth root of 2 to the 5th, which is just, I'm just going to say this, you just get 2. So you could have gone straight from this to 2, and I wouldn't mind. But on the top, we get the 5th root of, and we're going to put these things together. We get 3 to the 1st times 2 to the 3rd. So we can multiply all this back out again. This would be 3 times 8. It'd be the 5th root of 24, which is how you might see some people write it, 5th root of 24. I would advocate for just leaving it, factored like that. But that is how we expect to simplify radical expressions. Do not leave them in the basement, and remove any perfect nth roots. Cheers.